Okay, with the binomial taken care of, let's take a look at the actual parallel system reliability here. Okay, so the sum system implements a redundancy design. Okay, redundancy design that instead of using one component for the line, instead it is using 4 components to ensure the reliability. Therefore, that failure of one component does not lead to the failure of the overall system. So in this way, the overall reliability can be significantly improved. So if you think about the flight engine, right? I searched this, can airplane fly with one engine? The answer is certainly yes. Okay, so from this perspective, the airplane engine can also be considered as the redundancy design. Okay, so here, exercise number 3, let's take a look at together. Here we're looking at 4-component system that is using a parallel design or redundancy design, and each one of the components are assumed independent, and each of those components have a probability of failure of 5%, or the probability of up and running of 95%. Okay, how reliable is the system? In other words, we need to calculate the probability of this system up and running under some conditions. And rephrase, that is the probability of at least one component is working. At least one component is working. So we need to consider this. At least, no. This is asking at least one component is working. There are total 4 components working. So we need to consider exactly 1 is working, exactly 2 is working, exactly 3 is working, exactly 4 is working. So we need to combine all the probability, and this is going to be the answer for this question. Okay, or in other words, you can simply 1 minus P0. You got it? So originally, this is an exhaustive set. This considers all the possible scenarios related to the failure of the system. We're simply excluding exactly zero failure out of 4, because the question is asking probability of at least one component is working. So at least one component is working, that means that is the when the system is still reliable. Okay, that simply means we need to exclude probability of exactly 0 is working. I hope this makes sense to you. So since this simplifies our calculation greatly, what we can do here is 5, okay, power by 0, because we'd like to observe exactly 0 success, multiply by 0.05, remaining we have a 4 failure event. So if you calculate this and you subtract the result from 1, okay, if you subtract the result from 1, that is going to be the answer for this question, the reliability. Of course, I have a full solution coming in here. Yeah, so this calculation follows this. If I do a review here, this is number of success event, total number of event, and this is a probability of success. This should not use true, I'm sorry, I think this is typo. False. Yeah, false. So again, I've listed all the events here. Exact 0 failure. Again, you cannot go more than 4 because we only have 4 components in here. Okay, exact 0 failure, exact 1 failure, exact 2 failure. So when we talk about reliability, that means a state where at least 1 is up and running. That means everything falls into our description except 0. So probability of at least 1 function, okay, it's going to be this big in terms of the probability. I hope you got this example. This is a very short example, but it's very important. Okay, let's take a look at exercise number 4. Suppose that the failure rate for each component of a 3-component parallel system is 0.004. This is a lambda 0.004. That is what it is. What is the probability that this system will outsurvive the first 200 hours? Okay, so you can pause a moment and think about how to solve this problem. Okay, so of course, when you have the failure rate lambda, you can always calculate the reliability or the probability of surviving a certain point. So this is asking 3-component parallel system. Okay, so let me visualize this before I move on. This is a system like this. So we'd like to know what is the probability this system will all survive. This is the reliability of the system. Okay, this is going to be 1 minus P 0, exactly 0 working out of 3 components. Okay, but for that, you need to know what is the P, which is the success, the probability of success, and I think for that, you need to rely on lambda t. I hope you got the idea. Let's move on, take a look at the solution. So, because our lambda is 0.01 and 0.01, and MTTF is 100, and what is time bound? I think there's a slight mistake in here. Let's fix this as 100. Okay, instead of 200. So everything will be fixed then. So we'd like to consider first 100 hour. I think that's what it is. And the reliability of individual components is this. This can be calculated again. Okay, so lambda is 1 multiplied by 100. That's how you get it. So you plug it here, and you have obtained the probability of success for each component. But all the components will have the same probability of success, therefore that's all you need. Okay, so this is what we want to know, because eventually you want to do is 1 minus this particular value. Okay, so I mean, that's what I'm saying. As long as you understand the binomial probability part, this part is really, really easy. Okay, reliability beyond 100 hour is 63.21%. Okay, so lastly, let's consider the reliability of mixed series and parallel system. This is a mixed system that uses both series and parallel system. Okay, I think a system eventually when you simplify the system, eventually will become either parallel and series. Okay, so for example, this, although it looks like a mixed system, if you watch closely, you can simplify this part first. You can simplify this part by obtaining the reliability of this section by using the binomial distribution. And then it will turn into a series system that look like this. Okay, with series system with 4 components. So this, it can be calculated easily. If you still remember the exercise number 1, it is nothing but the multiplication of all of them. Okay, I think I'm not doing anything here because this is so simple. If you are wondering what's the overall probability, just multiply this number. 99, multiply 999, multiply 96, multiply 98. That will give you the reliability of this part. Here, what is the reliability of system A here? So this will eventually become a parallel system because this upper layer will eventually combine into 1, right? And lower layer will eventually still become the 1 component. So what they're seeing here is another parallel system. Okay, so again, can simplify into this type of parallel system. With a parallel system, you consider chance of both ABC failed and DE failed, and that probability is 1 minus this multiplied with 1 minus this. In other words, you are considering the chance where both of them are failed. This guy failed, and this guy also failed. As long as we rule out the chance that both of them have failed, and we can obtain the reliability of the overall system, which here is 99.69%. Okay, so it's fairly straightforward. So the key here is you need to know how to simplify a mixed system to either a series or parallel system. Okay, so let's take a look at the, I believe it's the last exercise. The single light bulb system has 10% probability of failing within the first 200 hours. How much is the improvement in terms of reliability when switching to a double light bulb system that uses exactly the same type of light bulb? Okay, so there are many things you can do with this description. Okay, so first thing, let's focus on what it is asking first. So the single light bulb system, like this, and then there is a parallel system this is referring to. Okay, and basically it is asking what is the difference in terms of reliability between these two systems. So reliability of this system is what? This is 10% of failing. Therefore, reliability of this system is actually 90%. Okay, it's 1 minus 10%, therefore 90%. We also get to know the individual component reliability, which is 90%. Okay, and what happens to the improvement? What happens to the reliability where we change this into the parallel system? Okay, here is what you're seeing. We got this already. Redundant component system. So when you are making it as a redundant system, you are interested in this, right? And whatever afterwards. Exactly 0 functioning out of 2, which is something you can obtain from here. Okay, and then it's 1 minus that probability. The reliability of the parallel system is 99%, where the single component system is actually 90%. The difference in terms of reliability or the amount of improvement is actually 9%, which I would say is pretty significant. You can easily translate it into some dollar value based on the context. Okay, so you can always think about whether the additional 9% improvement can justify the investment on the additional component. So I think that is the additional comment I'd like to make. So what you've been seeing from these 5 exercises is actually very, very key, the bare bone information that you need to calculate the reliability based on the higher level description of the system, whether it's a series, whether it's a parallel. Okay, but in real case, a lot of times the 1% is usually attached to some dollar value. So for example, let's say 9% improvement comes with $1 million expense. Okay, would you still want to do it? So you need to think about, you need to consider this from more from a business perspective, whether this type of system design is preferable or not. Okay, so I think this deals with alternative design problem type. So you often ended up comparing multiple different type of design in terms of determining information like this. What is improvement in the reliability department? So this kind of captures the key to each type of exercise we've done together so far. System reliability with exponential failure rate, redundant system reliability and redundant system failure rate, redundant system reliability with exponential failure rate. That's again the same thing. For this mixed system reliability, I did not make it as exercise, but this is very simple, so I left it as just a slide. Okay, And then we looked at the reliability for alternative design.